Okay, so the last part of this topic is about modelling with linear equations. And we haven't done, you haven't necessarily done modelling with quadratics just yet, but modelling is where you take something that is in the real world and you try and use maths as a model to be able to help you to predict things or to be able to understand the real world. And actually, there's a lot of modelling that has been happening in the world at the moment, all to do with the pandemic. And when you see things in the news that are predicting about how things will happen, that isn't someone just using a crystal ball and thinking what's happening next. That is mathematicians who are using models to try and think about how numbers will be changing in the COVID pandemic. So really, maths is incredibly important for humans to try and decide how things will happen and to make predictions about what will be occurring. So I've said here that in real life, lots of things have a quadratic relationship. So I've said here vertical height with time. You may not have done this bit just yet in quadratics, but if you are throwing a ball, the pathway that it moves when you throw a ball like across a field is a quadratic kind of curve. So there's some maths that it links up to. But actually a lot of real life variables have got a linear relationship. And this word linear relationship obviously is going to mean like sort of straight line graphs. Obviously that's the chapter that we're doing. Lots of things have a linear relationship. And what that means is that there is a fixed increase or decrease in one variable each time the other variable goes up by 1 unit. So for example, the car sales made and the take-home pay. Lots of people who sell cars will get their pay directly proportional to the number of cars that they sell. Things like the temperature and altitude in a particular location has a linear relationship that as the higher you get, what happens to the temperature? Colder. It gets colder, and that relationship is actually a linear relationship, which means that every time you go up, say, 10 meters, the temperature will have decreased by a fixed amount if you're in that same location. And also the relationship between Celsius and Fahrenheit. Obviously in the UK we use degrees Celsius, but in many other countries, particularly in America, they use Fahrenheit, and there is a linear relationship that you can use to convert between them. You may remember questions from GCSE where they would give you like a conversion graph, something that maybe looked like this, and you would use the conversion graph to be able to take you from one particular thing to another particular thing, often to do with like currencies as well. They have a linear relationship. And then I've said one that's just from like a maths kind of context. This is also going to be a linear relationship, that the nth term of an arithmetic series is linear. And you can see that this series is a linear series because each time that you move across one position, it is increasing, in this case, increasing by the same amount each time. And so we're going to try and use linear equations to help us model things in real life and to try and interpret things about these situations as well. So I've just got one example here of, well, it's altitude along the bottom, and it's the temperature, this time in degrees Fahrenheit. And it says that the temperature Y at different points on a mountain is recorded at different altitudes X. And they've drawn in a line of best fit here. And this line of best fit is going to be the linear model that they are using, the linear model of y equals mx plus c. Now we're going to try and determine, just by looking at the graph, some of the features of this linear model. And then what we're going to do in the next couple of examples is we're going to try and do it more accurately. So first of all, I want to determine what m and c are. And I've said that I can assume that the line goes through 0, 70 and 250, 20. So the line seems to be going through this point here and this point here. Now, if I wanted to find out what C is, that should be really easy to find out what the C part is. What is the C part?
70.
C is just going to be 70 because that is the intercept of where it actually crosses. Now, before we actually move away from this and go and find out what M is, I'm going to do part B, which wants us to interpret the meaning of M and C in this context. So to interpret something means to say, what does that number actually mean in this example? Not what does this number mean, oh, it's where it crosses the y-axis. What does this number mean in this particular example? Any suggestions of what this number actually means? Jamil?
C is when altitude is 0, what the temperature will be.
Good. So C being 70 means that when the altitude is 0, the model would predict that the temperature was 70 degrees. So C means when the altitude is 0 meters, the temperature is 70 degrees Fahrenheit according to the model. Now I've written that little extra phrase at the end saying according to the model because it doesn't mean that when you get to 0 meters that you would take out a thermometer and it would say 70 degrees Fahrenheit. And it doesn't mean that that will happen and that it's true in this particular scenario we've got here. It just means that our model would predict that to be true. And if I wanted to find out what m is for this particular bit that I've got here, how would I find out m if it's going through these two coordinates? Someone just tell me what the calculation would be to find out what the gradient is. Change in y, so I can do 70 minus 20
And then you do 0 minus 250.
and 0 minus 250. So that's 50 divided by minus 250, which is minus 1 over 5. Now, so far, it's been really, really useful to do everything as fractions because that's been in pure maths. We're now kind of stepping out of the pure maths section, and we're now trying to make it about real life. So if we're talking about things that are real life, our brains are usually a bit more familiar with measurements like Fahrenheit being in decimals. So we may use this as minus 0.2 instead because it's in a context of real life. So the value of m is minus 0.2. If you wrote minus a fifth, it would be perfectly correct, but I'm just trying to bring it into what the real life sort of bit means. And so what does the gradient actually mean in this context? I wonder if anybody can try and explain what that means. Andrew?
For each meter you gain in altitude, the temperature would decrease by 0.2 Fahrenheit.
Perfect. Couldn't say it better myself. For each meter that you increase in altitude, the temperature will decrease by will decrease by 0.2 degrees Fahrenheit. So I'm just going to write that down. For each meter you increase in altitude, the temperature decreases. It decreases because it's negative by 0.2 degrees Fahrenheit. Because that's what the definition of the gradient is. The gradient says, for each one space that you move along the x-axis, how is the y value changing? That's what the definition of the gradient is. We know it's negative because we can see it's negative just by looking at the graph as well. Just as a little side note, sometimes if the number is very small, and it is quite small here, it might be quite strange. Let's say it was a different number. It might be strange to say each 1 meter you move along, the temperature decreases by 0.02. That doesn't necessarily make much sense to a human because it's so small. You can also play around with the values. So for example here, if I was going to change this, I could say for every 10 meters that you increase in altitude, the temperature decreases by 2 degrees Fahrenheit. You could also proportionally have that relationship as true, just because sometimes that might be a better way to communicate things. But if you want to just say it for 1 meter, you're always going to get the mark. I'm just trying to talk about more of a real life context we've got here. Okay, so we actually know the equation of the line now. The equation of the line is y equals minus mx plus c. We've got minus 0.2x plus 70. And we want to predict at what altitude the temperature reaches 0 degrees Fahrenheit. So how would I predict what that temperature is going to be? Yep.
When x equals 0.
When x equals 0. I'm not sure if it's going to be when x equals 0, because when x is equal to 0 is when the altitude is 0. And we want to actually know what the temperature is going to be 0. Yeah, so the temperature is being measured here as y being equal to 0. So we would have 0 equals minus 0.2x plus 70. So just squeezing this in here, 0.2x equals 70. Multiplying both sides by 5 or dividing by 0.2, and you get 350 meters. So the prediction would be that when we get to 350 meters, we would think that the temperature would be 0 degrees Fahrenheit. Now, do you know the word that is, if we've got this amount of data that's here and we're trying to make a prediction that's outside of the data, do you remember what that word is that says we shouldn't really do this because it's unreliable to make that prediction? It begins with an E. Lily? Extrapolating, yeah, extrapolation. So if you're going outside of this range of data that you've got to make a prediction, so we're trying to make a prediction somewhere down here, we call this extrapolation. That means it's outside of the original range of data that you've got. If I wanted to make a prediction about 125 meters, that's a good value. That's called interpolation. And I like thinking of it as like, you know how inter means like inside, like interior, and extra would mean like outside. So it's inside the range or outside the range of things that you might be looking at, okay? So that's why it's a prediction. But with temperature, we don't know. You might get to a certain altitude and the relationship may no longer be linear. What does that mean, that the relationship may no longer be linear? I don't know if it would be random. It might give a different reading. So between here and here, it looks like a straight line. But later on, it may like curve. It may curve down. It may get really steep. It may flatten out. It may be that the temperature can't get any lower. So for the range we've got, it seems to be a linear model, but later on, it may not be a linear model, okay?
So,
yeah.
Can you give me the definition for extrapolation?
So extrapolation is making predictions outside the given range of data. And when I say the range of data, here I've been given information between 0 and 240 meters. So if I was going to make a prediction below sea level or above 240 meters, that would be considered extrapolation. So we're going to do one full example altogether, and then a second example that are both exam questions that you're going to do sort of in pairs, and then we'll come and see how that all comes back, okay? The hardest thing about these questions is they pop up in the middle of an exam, and you don't know what the topic is. It doesn't say to you, we've been doing straight lines for the last 4 lessons with Mr. Bison. You're going to have a straight line exam question like immediately. You have to try and determine what the topic is. So we're going to look at this question and we're going to try and think, first of all, how we know that this is going to be to do with straight lines. Okay, if you need to copy any of these notes up, I can come back to the page when we're doing some work. So we're going to read this question and I want to see if we can work out what is the part that is going to tell us that this is to do with straight line graphs. How is this going to be a chapter 5 topic? So we have here a tank which contained water started to leak from a hole in its base. The volume of water in the tank 24 minutes after the leak started was 4 meters cubed. So it was 24 minutes. The leak meant that there was only 4 meters cubed left. The volume of water in the tank 60 minutes after the leak started was 2.8 meters cubed. The volume of water, V meters cubed, in the tank T minutes after the leak started can be described by a linear model between V and T. What in the question so far would tell you that this was a straight line graph, a chapter 5 kind of exercise? Pardon? Linear model, okay? If you see linear model, this is only one option of what topic this can be. Linear model, straight line graphs, okay? You've got to try and have that in your head, that linear model means straight line graphs. But they haven't said y and x. Instead, they have said v and t. So I'm actually just going to draw a graph for a second. if you were going to try and draw a graph about the volume of water in a tank over time, what do you think you would like to put along the x-axis? The volume or the time? The time. Yeah, we always put the time along the bottom, okay? So this is where the time is going to be, and the volume is going to be where the y-axis is. This can often be really helpful to draw a sketch, and I would recommend, there are many ways of answering these questions, I would always recommend doing it this way, because it just becomes really easy, really, really quickly. So I like to draw a quick sketch to remind me which is the one I'm going to say is y, and which is the one that I'm going to say is the x part. And then I've got here some information. I know that the volume of water in the tank 24 minutes after the leak was 4. So I'm going to go along the t-axis. I'm going to do a sketch of this. I'm going to go to 24, and I'm going to say at that point, the volume was 4. So I've got a point here, and that point is 24, 4 as a coordinate. And then the volume of water in the tank 60 minutes after the leak started was 2.8. So again, it's just a sketch. It doesn't need to be in the perfectly, the best space, just roughly where it should be. It's now come down here to 2.8. So this coordinate is 60, 2.8. And they think that this relationship is going to be a linear model, which means that I should, in theory, be able to go to this graph, and I should just be able to say, okay, if it's a linear model, it's going to be a straight line. It might not be a linear model in real life, and we'll talk about that later, but they've asked us to do it as a linear model. And all it wants us to do for part A is to find an equation linking V with T. So what's it actually asking? Find the gradient of the line. And then you don't need to find the intercept, because remember the way we usually do it is we have the gradient and a point. Well, we've got a point. We just need to find out the gradient of the line, and then we'll just use the formula. So the first thing, thank you, Minhaj, is we're going to find out what the gradient is. So the gradient, we're using these two coordinates we've got here, which is 24, 4, and 60, 2.8. We're going to do the change in y, so I'm going to do 2.8 minus 4 divided by 60 minus 24. And I'm going to get my calculator.
It's minus 1 over 30.
So it's minus 1 over 30. Now, I probably would keep this one as a fraction, because as a decimal, you get a recurring decimal, and that's probably not what you want, okay? So it's better to leave this one like this. And so usually my formula is y minus y1 equals m brackets x minus x1. And this is where the graph is going to come in handy, because I'm not going to write y anymore. I'm going to be writing v. And I'm not going to be writing x anymore. I'm going to be writing t. So it's going to be v minus, I'm just going to use this first coordinate. So it's going to be v minus 4 equals minus 1 over 30. Not going to be x anymore, it's going to be t minus 24. And I am probably going to write it in a slightly better form than that. I'm going to do expanding the brackets. So I get v minus 4 equals minus 1 over 30 t. And then that's going to be plus 4 over 5, because 24 over 30 is 4 over 5. I'm then going to add 4 to that. So we get minus 1 over 30t plus 24 over 5. And that's it. That makes sense that this is the equation of the line. Can you tell me something about this that makes sense in the context of what this line looks like? What makes sense about it? What's good about this? It's a straight line, so we can tell there's nothing quadratic about this. What else is good about my values I've calculated that seems to make sense? It's negative. Tell me why that's important, Khadija. Shows the line is going down, and in the context of this question, it shows that the volume of the water is decreasing because water is leaking. And I've also got a positive y-intercept, and we're going to see what that y-intercept might be in just a second, okay? So it's only 4 marks here, but there was an exam question that my year 13s just did that was just like this. It's kind of easy, right? I had students who could do some of the hardest questions on the paper, but they couldn't do this one.
What?
They couldn't do this one because they hadn't been doing straight line graphs in every single lesson up until this point. They couldn't see what the topic was, and they got confused. So your job is going to be, when it comes up randomly, is to be able to see what the topic is. Okay, so now we've come up with the model. This is the model. We're going to use this model to find out the initial volume of water in the tank. So if we're trying to find initial, what does it mean initial? Yeah, Prabhat.
The start.
The start. And if it's the start, it's when t is equal to 0. Now you could just look at it and say what it is, but I like to say that t is equal to 0. So v is just going to be 24 over 5, which is 4.8 meters cubed. And then part 2 of the question, it wants us to find the time taken for the tank to empty. If it's the tank to empty, good, v is equal to 0. So my equation will be 0 equals minus 1 over 30t plus 24 over 5. So that's 1 over 30t equals 24 over 5. I'm going to multiply both sides by 30, and we get 144 minutes, hours, what is it? Minutes. It's all been in minutes, okay? So it's 144 minutes. You could give it in hours and minutes, but it's fine to just give it like this. And then this is the part that makes it like a modelling kind of question, because it says, suggest a reason why this linear model may not be suitable. Andrew?
Because it's assuming that the rate of water leaking wouldn't change when stuff like pressure did.
Yeah, excellent. This model is assuming that the water is leaking at a constant rate. Okay, this model is assuming that the water is leaking at a constant rate. So I'm just going to write that down, and then we're going to talk about that a bit more. So why this may not be suitable is the model assumes the water leaks at a constant rate which is unlikely. You don't have to say why, you just say the model says it's leaking at a constant rate, and it's probably not going to be leaking at a constant rate. That's what the model assumes. And you can think about this in real life. You've all must have a bath at home, or you've had a bath. When you take the plug out of the bath, the water at the beginning goes down much quicker than after half of the water has drained. And that's because of the pressure. Because when there's a lot of water in the bath, the water at the top is pushing down the water at the bottom to leave the plug much quicker. And at the end, it takes quite a long time for that last bit of the water to drain out. So it probably wouldn't be a linear model in real life. It's probably, when they pull a plug on this leak, it's probably going to shoot out loads really fast. And then later on, it's not going to be shooting out quite so fast. So it's probably not going to be a suitable model. So you're going to do something, and I want it to be exactly the same kind of process of this. You're going to be looking at a question for me now that is to do with a plant, okay? And this time, it's not going to be y and x, but we've got h meters and t years. And I have been told about this plant that 2 years after it was planted, the height was 1.43. 5 years after it was planted, the height of the plant was 3.23. So I want you first of all to find out an equation linking h with t. So I want to see a quick sketch of what this might look like. And then I want you to see whether you think you might be able to answer part B. So I'm going to give you a couple of minutes to do that yourself, and then I'm going to start putting my answers up on the board, and we'll talk about part B all together, okay? Yeah. Usually what it probably would say in the exam is it might say find an equation linking h with t in the form h equals. So just do that finishing off and just say what h is equal to for that as well. Mm-hmm. Yeah, if you did it in fractional form, that's perfectly fine. You would have had this. Either of these answers are acceptable. I probably did this just because it is in the context of the plant. Okay, so hopefully you've got to the equation that links h with t, and it asked for us to be a linear model, so this should tell us it was like this. It was actually a question about a tree that I gave to my year 13, so it was very, very similar to this one. And then suddenly, after part A, they give you this new piece of information that we're going to need to do something with, and it says that the height of the plant was approximately 55 centimeters when it was planted. Explain whether or not this fact supports the use of the linear model in part A. So what do you think this piece of information, what's like the numbers that we can pull out from this? There's a couple of things we want to test here. Prophet?
That's the y-intercept.
So this is what, well, that's not what the y-intercept is. That's what the plant was when it was planted. It's not quite the same thing because it might not be the y-intercept.
Oh.
It would, if it is the y-intercept, then it's a good model. But this isn't, they're not telling us this is the y-intercept. They're telling us that's how tall the plant was at the beginning. So
if we work out the point, it would be like 0.55.
We could, but isn't it better to say that, to look at the model and to decide what the model would have predicted the height, the plant's height to be at the beginning, and then just to compare it to this? Okay, so it's easier to look at the model and say, okay, well, the model is going to tell me how tall the plant was at the beginning, and let's just compare it to the reality. Don't try and make this thing go into the model. Instead, let the model tell you something, and then compare it to the reality instead. So if it's when it was planted, what value do I know? Time equals 0. Okay, so time equals 0 for part B. So if time is equal to 0, the height is equal to 0.6t plus 0.23. So the height is just equal to 0.23 meters or 23 centimeters. So the model says that the plant should have been 23 centimeters when it was planted, but it wasn't. It was 55 centimeters when it was planted. So do you think this supports the use of a linear model? Do you think this is a good model to use? No. So this doesn't support the use of a linear model as 23 centimeters is much smaller than 55 centimeters.
So if it was like 54 centimeters, what do you mean?
Yeah, so if it was like 50 centimeters, 53 centimeters, 60 centimeters, you might say, yeah, this does support the use of a linear model because it's very close. But 23 centimeters and 55 centimeters is pretty far off, okay? And this is probably how growth of plants and people actually is. Probably for a certain period of your life, your growth may have been linear. Every year, if you drew your height on the wall, it may have gone up by roughly the same amount. But we know that humans don't grow like that. Otherwise, 90-year-olds would be like as tall as buildings, okay? So we know that growth is not always going to be linear. And it's the same thing as plants. There may be parts of their journey that are linear, but then it might level off. And it may grow really quickly to begin with. So there may be sections of the plant growth which are linear, but there may be sections of it where it is curved or where it is completely flat. So there are different parts of its journey, okay? So what I'm going to want for you to do is the last exercise in this chapter, which is exercise 5H. I'm going to ask for us to do questions 5 to 9. And we might then be able to just start some bits on our next topic, which is vectors as well, okay?